So before I start, I'm going to tell you where I made mistakes before printing the thesis. And it is on page 21. It says on the 5th line from the end, it says static, but it's supposed to say deterministic. And then on page 99, it says table ? And it's supposed to say table 9.1 in two places. So, today I'm going to talk about my licentiate thesis, and it's called Mathematical Models for Optimizing Decision Support Systems in the Railway Industry. And as Marcus, you said, my main advisor is Marcus, and then the co-supervisor is Mikael Sjödin here, and Martin Aronsson is my industrial advisor or supervisor. And I work at 6 Swedish ICT, and I'm also part of the It's Easy research school here at Mälardalen University. And most of my research is funded by Trafikverket, where I'm part of this group called KITE. And we also get some funding from It's Easy. And today, I am first of all going to talk a little bit about why we do the research that we do. And then I'm very quickly going to go through my research questions and also the list of the papers that I have included in my thesis. And then I'm going to go through the papers a bit more carefully. First paper A, which is about replanning robustness, and then papers B to E, which is about shunting yard planning. And then I have one slide with all the conclusions. So, first of all, why do we do this? Well, the thing is that finding an optimal solution to infrastructure allocation problems in the railway industry is really very hard. Trafikverket gives out this little brochure where they talk about making timetables, and they say that you have to make a timetable with 1,500,000 trains and 2,200 maintenance works every year. So there's a lot of trains, there's a lot of maintenance works, and also the problem per se are hard. We prove that, for example, the shunting problem or the decision version of the shunting problem is NP hard. Actually NP complete. So it is hard, and currently most of the planning is done by hand, which means that it's a very hard problem when you try to do it by hand. So there's probably quite a lot of potential to be realized by actually using computers and decision support systems instead. And especially since the market is nowadays deregulated in Sweden, so you've got lots of operators that want to compete on, but also for the same infrastructure. So getting good decision support tools would be nice. So what we want to do is we want to develop algorithms and optimization models that can be part of such decision support systems. This is also an industrial PhD, which means that we sort of like have aimed at the Swedish railway industry when we developed our models and methods. There are a lot of algorithms and models that have been developed in the past, but few of them actually make it into implementation. So we try to make sure that what we do can actually be used. And we also try to make sure that we show what the gain is from using mathematics instead of doing planning by hand. So those two things have sort of like gone into my research questions, which can be found here. The first question is it feasible to use a mathematical programming model to generate a timetable that provides replanning robustness? And I'm going to talk a little bit more about that in a while. And then question 2 is about shunting instead. So can an optimizing mathematical programming model be used to construct a classification-able schedule with minimum shunting effort? And then there are 3 sort of like sub-questions. The first one being about whether we can use simple rules instead. And then the second one, B, is about whether we can also include the car order in the outbound trains in our models. And number 3 is about whether we can use rolling horizon planning and how sort of like the execution times are affected and also the shunting effort. So, these are the papers where we try to answer these questions. Where paper A answers to the first question and papers B to E answers question 2. And now I'm going to talk a little bit more about what we've actually done. So I'm going to start with paper A, which is about replanning robustness. And here we got a time geography graph. So we got geography on the y-axis and time on the x-axis. And we got two trains, the green train A, which starts at Q at 8 o'clock and then goes to M, where it arrives a little bit before 8:30. And then we got a red train B, which starts at M at like 8:08 and then goes to O, where it waits for a meeting with the green train, and then it keeps going and arrives to Q at 8:30. And this is the plan. This is how we planned it to be. But what always happens when you actually do things in real life is that the trains don't really arrive exactly like we want them to. So when we actually run the trains, the green train has been delayed. And if we still take the meeting at O, geography O, we're going to get a knock-on delay, because now the red train has to wait for a really long time and it's going to arrive at sort of like 8:35. But we have this geography P as well, and we sort of can tell that that is where they're going to meet if we just let them drive. So if we take the meeting at P instead, we can avoid the knock-on delay, and that is a good thing. So essentially the idea is that we want to construct a timetable where we have the maximum number of such alternative meeting points, and we also want them to be useful in some way, because if you've got lots of them very nearby, you might have many, but you still can't move very much time. So that is the main idea of paper A. And we do this by using a heuristic where we generate two timetables, an early one that we imagine being used as a sort of production timetable, and a late one, which is the sort of safety net. That is a solution that we know we can fall back onto if we end up in a delayed situation. And then we try to sort of like push those two apart as much as possible, either in terms of time or in terms of number of alternative meeting locations. Yes. This is the mathematical model that does that, or it's added onto a model for timetabling as well. So as I said, either maximize the difference in time, which is the first one, or we maximize number of alternative meeting locations, or links, which have start to end points that are alternative meeting locations. And this is sort of like what you end up with in the end. And here we got the early solution being, I think, slightly darker, and then the late one being here, and then the distance between them is sort of like the shaded area. So for example, up, I don't have anything to point with, but up there in the sort of like top left corner, we have a dark area where we've got alternative meeting locations. There we go. Tack. So here we got alternative meeting locations between the two solutions, but for example here, there is only one geography we can take the meeting, so that is sort of like a critical meeting that has to happen at exactly that geography. Yeah, and I said that we had two different objective functions, one that maximized time and one that maximized number of alternative meeting locations, is because what you want to do in real life is probably include both in the objective function so that you have many options, but also that the options actually help you, that you can move a lot of time by moving the meeting. And we tested our method on 2 different days, day 98 and day 101. And depending on which objective function we use, we do get different solutions. So figuring out what you want to do there is going to be important. So is it feasible to use a mathematical programming model to generate a timetable that provides replanning robustness? Well, yes, for a small track section, we can do this. But we haven't really devised an exact measure for replanning robustness yet. So that is sort of like where we're at. So that was paper E and replanning robustness. Now I'm going to talk about the freight train classification instead, so shunting yards. And shunting yards are yards where inbound trains come in, freight trains come in, and then you decouple the cars, and then you build new outbound trains. So the trains arrive to the arrival yard or the receiving yard, and then they are decoupled. They are rolled over a little hill. It's called a hump. And then the cars are sent to different tracks in the classification bowl where you build the new outbound freight trains, and then they depart either from the classification ball or they are coupled and move to the departure yard and wait there for their departure time. So in a very simplified example, we got the arrival yard to the left and the classification yard to the right. And here I've made each outbound train in a special color. And as you can see, we have 4 inbound trains, but we want to build 5 outbound trains. And we only have 4 tracks. So that is problematic. So what we do in Sweden is that we use mixing tracks, which is where we can put a mixture of cars to like a mixture of outbound trains. And then we have train formation tracks where we build the outbound trains. And on the train formation tracks, you're only allowed to have one train being built at any point in time. So only cars to one outbound train. So if we roll in the cars, then we put the red cars on the mixing track while we build the green, the orange and the purple train. And then we get to a point where the green and the orange train depart. And then we can do a pullback operation. So we pull back all the cars on the mixing track and roll them in again. And then we can build the blue and the red train on the mixing track, on the train formation tracks. And what we have done is that we have heuristics for the roll-in times. So when the trains are rolled in from the arrival yard, and we have heuristics that decide when we're going to do the pullbacks, and we have heuristics that decide when the trains are going to be rolled out from the classification track. And then we try to minimize the number of cars that are pulled back from the mixing track. Because whenever you do a pullback, that is going to be effort that you would rather not do. So we try to minimize the number of pullbacks, which equals minimizing the number of roll-ins. So we want to find the classification ball schedule that minimizes the number of car roll-ins while respecting all the physical, operational, and time constraints. And we have done a number of different mathematical models for this, and we try it on real data from Hallsberg, which is the largest shunting yard in Sweden. We have data from 5 months, and we solve the problem using Python for the pre-processing, and then Skip and Cplex for optimization. So this is the first mathematical program that we tried out. And basically what this one does is that it chooses a track and a start allocation time for every train. It turns out that it was not an amazing model. In green we have the average execution time, and we put a maximum execution time limit of 20 minutes. And in purple we have the worst gap at our execution time limit. So it's sort of like how far away from the best solution that the solution returned is. And as we can see here, it was 100% away, which means that we have no clue how close it is. So we made a different model, or Florian did. And this is a column generation model instead. So here we have sequences of trains that we fit onto tracks, and they would generate new sequences that are good given the problem. So this one worked a lot better. It always returned the optimal solution within our 20 minutes, and it also generally solved the problem faster. So can an optimizing mathematical program model be used to construct a classification ball schedule with minimum shunting effort? Well, the results from our test runs using real data from Hallsberg indicate that the column generation one actually can generate optimal shunting yard schedules for 5 days within 20 minutes, which we consider to be an acceptable amount of time. A problem is that you are going to need computers if you are going to use optimization. It's not anything you do in your head. So we also sort of like wanted to test if we could use some simple rules for generating this classification schedule and see how good they were. And we tested 2 different kinds of rules. A first come, first served, which is simply that when a car is rolled in, if there is an available track for that car, we roll it to that track, or if it's currently being built, its train is currently being built, we send it to that track, but otherwise we send it to a track that's available. And also we have a time limit strategy, which basically says that if your train is going to depart for 26 hours or 28 hours or 30 hours or later, then we're going to send you to the mixing track, and otherwise we do first come, first served. When we use these heuristics, we're going to run into a problem with infeasible schedules. And for example, if you do first come, first served on the example I showed earlier, you're going to end up with the green and the blue train on the mixing track when the green train departs. So we're going to miss green cars. So that is a way in which we can end up with an infeasible schedule. We might also have an infeasible schedule because the mixing track capacity isn't respected. So for this simulation study, we counted the number of times we ended up with infeasible schedules, and we also counted the number of extra car roll-ins as sort of like a measure of the schedule efficiency. And we tested this both in a stochastic and in a deterministic simulation, and the results I'm going to show is from the stochastic simulation. And here we have the number of times that we ended up with at least one infeasible schedule, so the number of times when we used more mixing track capacity than available. And this never happens for the optimization model because it forces the problem to be feasible. But when it comes to the simple route, it happens quite a lot of time, but the time limit of 32 seems to be potentially the best one. And then we looked at the number of missed cars, that is, the number of cars that didn't make it onto its outbound trains. And here, since we delay the cars, we sometimes actually don't roll in the car until after it has to be rolled out. So then we obviously can't get it on that train. And that's the red parts of the bars. And then the green are cars that we should have been able to get on the outbound train. And once again, the optimization model never misses any cars that could have made it with its outbound train. But the simple rules do, and 32 is once again, the time limit of 32 is once again potentially the best one. And then we look at the average number of car pullbacks, where obviously if we always send cars to the mixing track because of a tight time limit, we're going to have a lot of cars on the mixing tracks, and that sort of goes down. But it might be worth noticing that this time limit of 32, which sort of like was the best one when it came to feasibility, still uses about 5 times as much shunting effort as the optimal solution. So when it comes to the question of how effective the simple dispatching rules are, we'd say that they are not very effective. They generate infeasible schedules quite a lot and use a lot more shunting effort. So, paper D. Up until now, we haven't cared about the car order of the outbound trains, but this is what we do in paper D. So now, but from colors, there's also a number in every car. And we want to build trains which have the numbers in the correct order. So it doesn't matter, like for example, for this green train, there's 3 cars with number 1. It doesn't matter, that order within the 1 group doesn't matter, but we want all the 1 trains to be before all the 2 and 3 trains. I'm going in the wrong direction. So we want to change our model to take this into account. And the main thing with having to sort the cars within the outbound trains is that we are going to require more mixing because we are going to have to sort more. And when we need more mixing, some of the trains that could previously be scheduled after each other can't anymore because we need more pullbacks. And also we need new calculations for the mixing cost and the mixing length, which also gives us new arc weights in the subproblem graph for the column generation model, which is the one that we extended for block trains. So we did that, and these are the results that we get. Once again, we always find the optimal solution within 20 minutes, and it actually goes about as fast, so we're not too worried about the execution time. When it comes to the total number of pullbacks, when we have block trains, that is when we have orders in the outbound trains, we do need a lot more pullbacks, as I said. But the number of extra pullbacks that are required by the capacity constraints, that is if we sort of like take away all the sorting that we have to do to get the cars in the right order, that isn't too much, actually. That hasn't increased. So when it comes to this question, whether we can extend the optimization model to also include the car order in outbound trains, we would say that yes, we can do that. We can extend the column generation model, and the execution times aren't affected that much. But obviously we are going to need to do more shunting, but not because of capacity constraints, but because we need to sort the cars. So, welcome. Now we're up to the final paper where we do 2 things. we implement a rolling horizon framework, and we also implement a better IP model, because there was a master's student in Germany who I think was originally employed to look at the symmetry, but who instead came up with a new IP model that seemed promising, and it was very promising. So first of all, rolling horizon. It's when you do rolling horizon planning, you plan for 5 days, and then you finalize sort of like the first day, and then you move 1 day forward, and then you plan for day 2 to 6, and then you make sure that the solutions fit in the sort of like where they meet. And this is what we've done to be able to generate very long schedules, potentially infinite. And this is a heuristic, so we might not end up with the optimal solution anymore, but we still need to do something to be able to deal with time. And then this is the arc-indexed program, that is the new model, which basically looks upon the problem as trains that have to always have a train preceding them and succeeding them, and then solves it in that way instead. And this is the execution time for the arc-indexed. So we see that it is faster than the column generation, and it also always returns the optimal solution within our execution time limit. And when it comes to rolling horizon, we took away the execution time limit, so they always were forced to return the optimal solution before we're done. But once again, we see that the arc-indexed is a lot faster than the column generation. So is rolling horizon planning a feasible method for generating long time period schedules? Well, yes, we can use it for that, and especially the arc-indexed one is good because the execution time isn't increased. And also, sort of like going back to question 2 again, can we use mathematical modeling to solve the shunting, the classification ball schedule problem? And yes, we can, and you probably want to use the final arc-index model because that one is the fastest. So, as a conclusion, what we wanted to do was that we wanted to develop algorithms and optimization models that could be used to support planning in the Swedish railway industry. We have done this in 2 different ways. We have done it for replanning robustness. We had a MIP that generated a timetable that had some degree of replanning robustness. And we also have done this for the classification ball planning problem, where we have presented various integer programs for solving this problem, and also extended them for blocked outbound trains and implemented a rolling horizon framework. And it seems to be going fast enough to actually be usable. So that is all I've got.
Okay, thank you very much, Sara. So we will take